Hello guys, welcome back to Maison African Motives, still working on electrical trade theory and two in this platform. We shall be focusing on a full paper. We want to work out the full paper of February 2022, that is the X paper, which was written from 9 to 12, so that we can see how do they ask its typical questions for our revisions for the finals that we are about to have. So make sure you read your instructions, everything, guys. You read everything, especially the instructions and so forth. All right. So it's very, very important that you read and you understand the instructions that you're given for that question paper. All right. So in this case, we are given the first part of the paper, which is question number 1 on alternating current theory, that is the AC circuit theory. We are given the first part that was to define on 1.1. So 1.1 is to define the first part, that is the average value in this case. How do we find the average value, or what is the definition for the average value? So the average value can be given as the average of all instantaneous values over one cycle. That is the average value, the average of all the instantaneous values over one cycle. All right, so that is what we have in this case. We move on to the other part, that is 1.12, which is the form factor, having 2 marks, just like the previous part. All right, so the form factor can be taken from the RMS value as the ratio of the RMS value of a wave to its average. So that means we have the form factor in this case, which can be the RMS of the voltage over the average value of the voltage, whatever that you are given. You are dealing with the RMS and the average value in this case. That is the ratio between the two. That is your form factor. 1.2, we are given to name 2 effects of a low power factor. Whenever you are having a low power factor, what are the effects on the circuit? Okay, so we are going to have increased copper losses. All right, it reduces the efficiency of the plant. Thicker cables are required. It costs consumers more for the same load. If you're having the same load, but it costs the consumers, it limits the output of both generators and transformers. It draws more current from the supply. So we just have any two from these points that we have, so that we can, which are necessary, any two that we have can be part of our effects in this part. All right, we are now given on this part. I'm just going to take the information directly from this part. We are given that a conductor of length 85 millimeters. So we're given the length of the conductor in this case, which is 85 millimeters. But remember, milli means to the exponent of -3. So this is going to be 85 times 10 to the exponent of -3 in meters, or we can write this as 0.085 in meters, or 85 times 10 to the power of -3. It rotates through a magnetic field at a velocity of, so we are given the velocity at this for this rotation, that is 25 meters per second. Then we are given the flux density of the field is, so we are given B, which is our flux density in this case, that's 0.9 Tesla. The first question is to calculate the maximum EMF induced in the conductor. All right, so this we can calculate. Remember that the maximum EMF, which is given as E max, can be calculated from the product of B LV sine of what? Sine of theta. So that is taken at 90 degrees in this case. All right, so in this case we are not given like the angle, so we take this one at 90 degrees. So this is going to be B, which is 0.9 times the length in meters, which is 85 times 10 to the exponent of -3, or you use this decimal, just one and the same, times the velocity in meters per second, which is 25 times the sine of 90 degrees, which is same as 1. So it's just same as you're multiplying 2 to 1, which means there is no effect, even if we are not having this sign of theta. When the angle is not given, it does not affect your answer, okay? So this is going to give us something like 1,9. That's 1,9125, which we round off to 3 decimal place, is going to give us it. All right, these answers were to 1 decimal place. All right, so it's going to be 1,9 volts to 2 decimal places. All right, so that was the instruction. So you follow the instruction of the question paper. Answer must be given to 2 decimals, okay, to 2 decimals, unless you are indicated otherwise. So you work with the what you are given for that question, but mostly is 3 decimal places, but this one is to 2 decimal places, so it's going to be 1,9 volts. All right, the instantaneous EMF when the conductor is 60 degrees to the plane of the magnetic field. So this time we need the instantaneous EMF. Remember, the instantaneous values, these are values which are taken at a certain point. So this is equivalent to, we just write as E. So this is 1.32. So E is equivalent to E max times the sine of the angle that is given, which is sine alpha or sine theta. That is our maximum voltage, which is 1,91 times the sine of 60 degrees in this case. All right, so we can multiply this, that is the product of the two. So let's just check what we have. 1,1 times sine of 60 degrees. That is going to be, all right, so let's see, 1,91 times the sine. We use this one to 2 decimal places, the one that we got, times the sine of 60 degrees. All right, this is going to be 1,65. Okay, so we're going to have 1,65 to 2 decimal places, 1,65 volts in this case. So we take note of the instruction that we are given. The question is saying the instruction was to 2 decimal places, whatever answer that you're going to have. So you're going to leave to 2 decimal places as per instruction. All right. On question 2, you're given that on conductors, insulators, and cables. Cables are usually joined by using splicing kits. State 6 steps to be followed when making a joint, a cable joint. Okay, what are the steps that be taken when making or having a cable joint in this case? So that is the question that we are given. All right, so I'm just going to show you what we are given in this part, the steps that you're going to take. First part, ensure that cables are isolated. All right, prepare the ends for joining. So I'm going to prepare the ends for joining, then join the conductors using crimped frills in this case. Then insulate each conductor, reshield, and re-jacket. So this is the major part, the major steps that we are to take for a consideration of what? Of making a joint cable in this case. All right, so that is what we had. Let's check what we are given on question 2.2. Which is calculate the maximum fault current. All right, so this is about the fault current. All right, so that's 2.2. We are given to calculate the maximum fault current that we are given area of the cable in this case. So take note, if you are calculating fault current, all right, the formula you're also given in your formula sheet, that the fault current is equal to the copper insulation, copper and insulation factor. So you're going to have the copper and insulation factor times the area over the square root of time in this case. So this is your copper and insulation factor. This is your area, which is in square millimeters. Take note this time, area in square millimeters. This is your time in seconds. All right, so we are given that to calculate the maximum fault current, that a 10 square millimeters, this is area. So we are given area, which is 10 square millimeters. Cable can carry for a period of 4 seconds, which is we are given time. So we are given our time as 4 seconds. The cable is aluminum conductors with XLP insulation. All right, so in this case, we are dealing with the insulation that is for aluminum and for XLP insulation. All right. So if we are to check here on our tab, on our information sheet, all right, let's check here what do we have. All right, so this is what we are given. All right, so this is what we are given in this case. This is the formula. All right, where is it? Where is it? All right, where is it? Where is it? Okay, let me check this part. All right, this is our formula that we have. So this value that we are given at this point, that is our copper and insulation factor. You take it from the information that we are given. We are given the insulation, which is our XLPE. Then we are given the conductor, which is aluminum in this case. All right. So we are given this as aluminum. So the copper and insulation factor for this is at 92. So this is the one that we are going to use. So take note, the insulation and the conductor. All right. So this is the insulation. This is the conductor in this case. These two, they are at 92 for the what? For the copper and insulation factor. All right. So we're going to apply 92. So I hope we saw our formula, the one that we are using in this case. So this is the one that we are having here. So meaning to say our CIF is going to be equal to 92. All right, so we can calculate the copper, meaning the total current, which is the maximum fault current in this case. So our maximum fault current is going to be equivalent to 92 times our area, I said, in square millimeters. So there's no need for you to change this one, over the square root of time, which is the square root of t. Our t is the time in seconds, which is 4. So we can substitute everything to calculate our current. So this is going to give us something like 460. So that's 460 in amps. Take note about the units. If you write wrong units, then everything that you're dealing here is wrong. So make sure that you use correct units. All right. So that was our question. On 2.3, we are now given to state 3 factors that will influence the choice of a cable for a particular application. 3 marks for that. If you are dealing with the choice of a cable, what is it that is required? All right. So I've got these ones, which we have the circuit protection used. So we can work with the protection of the circuit, the cable length, the maximum load, the minimum power factor, the potential short circuit current, the exposure to the elements, and also the permissible voltage drop. So these are the factors that you are supposed to consider whenever you are to choose a cable for any application. All right, so that was our question 2, having a total of 12 marks, everything on question 2. On question 3, we are given now on switch gears. So we've got switch gear and protective devices. All right, we have got indicate whether the following statements are true or false by writing only true or false next to the question number from 3.11 up to 3.14 in the answer book. Okay, so it's all about the theory, guys. The theory part you have to revise also with your textbooks, and the more you work with your theory part, you see even, does this part make sense or not? So that is how we can actually attempt these typical questions. All right. So we're given 3.11 that a tungsten is the best conductor of electricity. That a tungsten is it. I don't know how you pronounce this one. So no, this one is actually false there. So it's not a good conductor. All right, it's not the best conductor that we can have. 3.12, a circuit breaker may be used as a local switch disconnector if it complies with the standards of a disconnector. A circuit breaker may be used as a local switch disconnector. If it complies, yes, it can be used, which is actually true for disconnection, switch disconnector. This is actually true. It can be used as a switch disconnector. 3.13, the overcurrent protection device protecting a three-phase motor must allow the motor to continue writing if single phase okay. This is false, all right? This is false, all right? Overcurrent, overcurrent is defined as current that flows when a short circuit flows. Overload current when a short circuit, no, this is false. That's false here. This can be an overload current is actually affecting on the what, on the load. So here they're saying when a short circuit occurs, no, that's not it can't be an overload. Okay, it can't be like an overload. Because this one, it is a condition when you are having like you applying an appliance which has got an overrating than the one that is required for that circuit. That is where we have an overload. Then a short circuit is on a condition whereby we can have a short or any connection that is not proper. It's all about the connection. That is the one that affects what, a short circuit. The overload is about what you are putting there. Is it of the same rating, or it's more than the one that is what required? Okay, so that is what we have in this case. 3.2, explain the operation of thermal magnetic type circuit breaker under a short circuit condition. A thermal magnetic type. Okay, so a thermal magnetic type can be given as let's have this one. The large fault current turns the solenoid into a strong electromagnet, attracting the ion armature, pushing a non-conductive link against the switch to the circuit. That is tripping while placed before the large fault current reaches the metal strip. So that is the condition that we have when on the operation of a thermal magnetic type circuit breaker. All right, let's check what we have on 3.3. State the function of a day-night switch. Okay, so this is actually repetition. 2022, they've been repeating this question. November, we had this question. July, August, we had also same question on the day-night switch. Okay, so this is what we have. Sometimes we can even take from the previous one that we talked about, that it can be used to automatically switch on lights, and that is to keep lights on during the night, and then switch them off light at dawn. If you are to check, okay, it's only that I am no longer having this other part where I was explaining to say the issue is on during the day when we are having the light, then it goes off. All right. Then at night, when there is no light, it senses that there is no light, then it goes on. So that is the operation that is simply happening in this case. So you can even relate to other operations that I mentioned before, so that you can pick which one is best. Sometimes, you know, these guys, they can change here and there, but you pick which one is best for you. All right. On question 4, this is now on batteries, where we are given on 4.1 to list 5 factors to be considered regarding the care of lead acid batteries. What do you consider that is taking care of the lead acid batteries in this case? All right. So we've got 1, we have to check the level of the electrolyte must be checked regularly and kept above the plates by topping up the battery with distilled water. Caution must be exercised due to high explosive hydrogen gas given off during the charging process. Remove terminal conductors when storing batteries. Also, to keep terminals clean, to keep the temperature below 40 degrees Celsius, and do not add acid to the battery. And also to keep the vent holes in the filler plugs open. So any 5 was going to be considered. In this case, we are given to consider 5 factors, so any 5 from there. All right, 4.2, briefly explain the term relative density, and this is 2 marks for this one. All right. So the relative density can be given as the ratio of the density of an electrolyte to the density of the same volume of water. That is the relative density. The ratio of what? Density of an electrolyte to the density of the same volume of water. All right. So that was 2 marks for that definition. Then to state 3 disadvantages of lithium ion batteries. That's 3 marks. Like I was saying, this one is also a repetition from same year 2022. All right. So the disadvantage that we have is sensitive to overcharging. It is expensive. Safety concern, that is explodes when overheated. So in terms of safety, it is actually need tight circuit because it can explode when it is overheated. Okay, it is sensitive to high temperatures. Also, transport challenges, limited quantities by air travel. So in terms of travel, in terms of transporting, there are so many challenges which are occurred in this part. So any 3 was actually going to be acceptable in this part on the disadvantages of lithium ion batteries. So that was 10 marks on this question on batteries. On question 4, that is now on question 5, we are given a condition on DC machines. So these are DC machines having a total of 10 marks. So everything is direct here. We are given 5.1 to explain the purpose of the following components found in the faceplate starter. So remember that the faceplate starter actually is there for the starting purposes to reduce or to limit the high currents which are needed. So in this case, we are asked to explain the purpose of these components which are part of the circuit 5.11. That is the no voltage relay, that is the NVR, the no voltage relay. What is the purpose of the no voltage relay? So the no voltage relay is used on a condition where it automatically disconnects the motor from the supply if the supply voltage drops below the rated value. So it is there to automatically disconnect the motor from a condition where the supply voltage has dropped below the rated value. Then it is in action for that. All right, so that is what we had on 5.12, the overload relay. Okay, same 2 marks. As you can see, each part is having 2 marks. So the overload relay, this is what we have got in this case. It is it automatically disconnects the motor from supply if there is an overload or a short circuit. So in case of an overload or a short circuit, then we can apply or we can get the use of an overload relay. That is the purpose of our overload relay, to automatically disconnect the motor on a condition of an overload or an open circuit or a short circuit, I mean. So on 5.2, with the aid of 2 circuit diagrams, show how a change in direction of rotation of a shunt motor is achieved. Indicate the current flow in both circuits. So we're asked to represent both circuits, the direction of rotation of a shunt motor. Okay, how the shunt motor is achieved in terms of rotation. All right, so this is what we got for the first part, a shunt motor. So in this case, the marks are on the supply to indicate the supply, the direction of the current, that is your field current, and also the armature current in this case. All right, and the reversing of the field current in this case. All right, so that is the first part. And on the other part now, the direction of the current, which is our field current, and also the armature current that is reversing. Also, these two, they will be reversing. So as we had here, as the field current is going up, the armature is going down. So these two, they are opposing. Now this is going up, this is going. So the reversing part is the one that you are being asked in this case. Can you clearly show this reversing part in this case? All right. So the question is for you to clearly show to indicate the current flow. This is the most important part. All right. So that was actually 6 marks in order for you to have these diagrams, which means it's an advantage also to know diagrams in electrical trade theory. On question 6, which is on AC theory, you are given a wound motor. A used motor is all right. So this is a wound rotor, or not motor, sorry. A wound rotor induction motor is widely used to drive large mechanical loads. State how the rotor windings of these motors are connected. So how do you connect the rotor windings in order to achieve this? So this is in delta, not delta, but star. Guys, okay, this is a star connection. All right, so these are connected in star. Then how are the large starting currents limited? How do we, all right, we are dealing with the limit of current. So how are the large starting currents limited? How are you going to limit the large starting currents? All right, so what I'm having here is by adding the resistors in series with the rotor windings to produce a high starting torque and to control the speed of the motor. That is what we have in this case. So it's actually just 2 marks for that. But it's very, very important. 2 marks is a lot in exam. Show by means of a circuit diagram. So here we need the circuit diagram, how the starter windings of a 3-phase induction motor are connected in delta. Take note, in delta. And it's a 3-phase induction motor in this case. All right, so this is what I'm having in this case. We have got 2 diagrams. You can pick from any of these 2 in delta, but the most used one is this last part that we have in delta from the line currents. All right, or we can even use the first one depending with your understanding in terms of what, in terms of diagram, because some of us, we want complicated diagrams. Some of us, we want simple diagrams. So you just pick which one is best for you. On 6.3, we are given now to name 2 applications of a capacitor start and the capacitor run induction motors. Also, this one, I talked about it previously. We've got issues of washing machines, lawn mowers, swimming pool pumps. These can be applications, so many applications that we can have. So we just have to list any 2 from the given, or if we have any other applications, let us also list them so that it can be of advantage to others in revisions. Next time we can list those in other questions which follow. Okay, briefly explain on question 7, which is on transformers. We are asked to briefly explain the difference between the magnetizing component and the core loss component of no load current of a transformer. What are the differences between the 2, the magnetizing and the core loss? Okay, so on the magnetizing component, we are saying it is 90 out of phase, that is 90 degrees out of phase with respect to the applied primary voltage, and the function is to produce the magnetic flux. So this is to produce or to give us the magnetic flux, whereas the core loss component is in phase with the applied voltage, and its function is to supply the iron loss, that is the constant loss, as well as the small copper loss occurring in the primary winding. So these are the differences, or the ones that we have, or what can you say, the differences between, all right, or the comparison that we can have between the 2, the magnetizing component and the core loss. So it was actually 4 marks, meaning to say each part is having 2 marks in this case. All right, so that's 4 marks for everything on question 7.1. On 7.2, we are given the secondary voltage of 100 kVA. So we're given the rating of a transformer in this case, which is our S, which is apparent power. In this case, we are given 100 kVA, that is volt amperes. single phase. Take note, it's a single phase ideal transformer. So it's a single phase ideal transformer with 220 volts when the supply to the transformer is 11 kilovolts. Okay, so we're given it's a single phase. The secondary voltage of A, okay, so the secondary voltage is 220, so which is V2, or you can write as VS, 220 volts. While the supply it's 11K, so the supply it's your V1. This is your input, which is 11,000. Kilo means 1,000, so that's 11,000 volts. So the reason why we are using V1, V2, and so forth is we just use according to what we are given on your formula sheet here. We are given on transformers V1, V2, V1 for the primary, V2 for the secondary. So you can use, yes, VP and VS, it's fine, but I'm just going to use what you are related to with your formula sheet, so that when I'm writing the formulas, you just relate to the ones that you're given. All right. So here we are given, that's what you're only given. The first part of the question is to determine or to calculate the turns ratio. So take note, the turns ratio, that's 7.21. So turns ratio can be taken from the ratio of N1 over N2. But we do not have N1 and N2, but we know that N1 and N2 is also equal to V1 over V2, which is also equal to I2 over I1. So we just refer to what we are given. We have got the voltages, so which means we are going to take this part of the voltages, which can give us what? The turns ratio. So which means N1 over N2 is equal to V1 over V2 in this case. So you can substitute the values that we are given. V1 over V2, our V1, that is the primary, which is 11,000 volts, over the secondary voltage, which is 220 in this case. All right, so that means N1 over N2 is going to give us 50. All right, so that's 50 over 1, or 50:1. So we can even write this as a ratio. N1 as to N2 is equal to 50:1. This is same as 50 over 1, so it's a 50:1 like this. So you can even write your ratio like that. A transformer ratio can also be given as a whole number, or you can give it in this, so you can write it in this form, which is just one and the same thing. All right, the value of the primary current at full load. So what is going to be the primary current at full load, which means we have to calculate I1 in this case, that is primary is represented by 1. So take note, in this case, we are given the apparent power in this case, which is V1 times I1. We have this apparent power S, which is equivalent to the product of what? The product of voltage and current. So it can help us to calculate I1, that is in this case. So this can help us to calculate I1, since we are given S, which is equal to V1 I1. We can substitute these values, which is also equal to V2 I2. But since we are focusing on I1, we have to use this one. All right, so we can substitute our values. Our S, which is our apparent power, is given as 100 kV, which is 100,000. Kilo means 1,000, so this is 100,000, which is equal to V1, which is 11,000. So we've got 11,000 times I1. So you can divide by 11,000 both sides, so that we remain with I1 in this case. All right, so dividing by 11,000 each term, we are going to obtain something like 9,09 and so forth. So it's going to be 9,0909. So that is what is going to repeat and so on. So to 2 decimal places, we are going to have this. Remember, we are told to 2 decimal places. We're going to leave this one as 9.09 to 2 decimal places. All right. Then the maximum secondary current. So like I was saying, in this case, we can even use the formula for S, which is equal to V2 times I2. So that means we can also calculate the I2 in this case from V2 times I2 from the same S that we had. So this is 7.23. So remember that our apparent power can also be given as V2 times I2. So you can substitute apparent power being 100,000, that is 100 kVA. So it's 100,000 is equal to V2, which is 220. So this can help us to calculate I2. If we divide by 220, since you are multiplying, we can have the value for I2 in this case. All right, so that is our current I2, the current in the secondary, okay? So 100,000 divided by 220 is going to give us 554. So not 500, but 454, comma, 5454, and so on. So it's going to be 554, 554. So this 5 is going to change this 4 into a 5 to 2 decimal places. Remember, as per instruction, to 2 decimal places. So that is what you're going to have as the current in the secondary that is at full load. All right. So this is what we had. These are the typical questions. That is how they can actually ask these questions. You have to be careful. Also working with your formula sheet, the formulas you are given. So all what is needed is to apply your formulas properly. All right. On question 10, question 8, which is on earthing, that is 8.1, we were given to briefly explain what you understand by a floating earth. If we are talking about a floating earth, what do you understand by that? And this is actually 2 marks, all right? So a floating earth in this case can be given as it results when there is no electrical connection between a portable electrical appliance and the earthing system of the supply. So when there is no electrical connection, that is where we have what we talk as the floating earth in this case. All right. So that is what we had. That is 2 marks for that. And on 8.2, we are given what does SANS 10.142 stipulate with regards to wiring armoring of a cable as an earth continuity conductor, the bonding of a hot and cold water system. So we are referring to the what, to the sense values or the regulations that we are given in this case. So when dealing with the wire armoring of a cable as an earth continuity conductor, this is what we are given. All right. So the wire armoring of an armored cable may be used as an earth continuity conductor as long as it complies with the requirements of the SANS 10.142. So this is what is important, as it complies, as long it is in requirements that you are given, then it can be used as given. All right, so that is what we have, which is the same thing as the 8.22 on the bonding of a hot and cold water system. All right, so you've got the bonding of a hot and cold water system. All right, so this is what we have in this case. What is needed is the hot and water system shall be bonded together and also be bonded to earth continuity conductor system. So it must be also be bonded to earth continuity conductor system. All right, so this is 2 marks each. All right, then what about the leakage currents? Also 2 marks for this one. So for the leakage currents, what is important is that people, animals, and property shall be protected against harmful earth fault currents by protective measures such as the use of earth leakage protection for socket outlet circuits. So if you're dealing with leakage current, everything must be protected from earth leakages, okay? That might happen, which is the earth fault currents in this case, all right? That is according to the SANS 10.142 stipulation or regulations. All right, so I don't know how you actually do pronounce it and how do you read or specify, because differs. Okay, on 8.3, how is earthing done for overhead lines? If we are dealing with overhead lines, how is earthing done? Okay, how do we apply the issue of earthing? Okay, so here I've got this part: by installing a bare earth conductor above the overhead lines, which is grounded. So by installing a bare earth, so once you've got a bare earth or a naked earth, then it can actually help in issue of what? in the issue of overhead lines, that is earthing of overhead lines in this case. All right. So that was our question 8, having a total of 10 marks. On question number 9, which is on measuring instruments, we are given with the aid of a circuit diagram, show how a watt meter is connected to a high voltage circuit, which is actually 3 marks. So a watt meter can be connected as follows. This is what I'm having here, where we are given our watt meter at this point. We're having the voltage coil, the primary coil, the potential transformer, the current transformer. So these are the major parts that are needed in order for you to obtain the 3 marks. Okay, so that is what we had in this case. If we check the other part of the question on 9.2, we are given a galvanometer with an internal resistance. So this is just a measuring instrument that you're given, which has got an internal resistance of 50 ohms and gives a full scale deflection of this current. So take note, calculate the value of the shunt resistor. Here they told you, but whenever the instrument is used or the meter is used for measuring currents, you are to use a shunt resistor. All right. If it is used to measure voltages from 0 to 50, whatever that you are given, then you use a multiplier resistor or a series resistor on that condition. All right. So in this case, it's current. So which means we are going to apply or to use a shunt resistor. Remember, a shunt resistor is in parallel. So we've got a meter. In this case, this is how our diagram was going to look like. So we have got the meter in this case, which is at full scale deflection. And now we have connected a shunt resistor in parallel to measure a current, which is the total current in this case that is going to be at this point. All right, so we have our total current to be measured, which is 1,5 here. It is to measure a current of 1,5 amps. So this is our total current of 1,5 amps. But remember that on this part, this meter is at full scale deflection. It has its own current that it must accommodate. So this is the current of or across the meter of 10 milliamps at full scale deflection. So we've got 10 milliamps in this case. So this is at 10 milliamps. So we need the current that is going to be under, that is going to flow through the shunt resistor in this case, just like what we saw on the meter. This meter is having an internal resistance of 50 ohms here. The internal resistance is of the meter. So this is our meter, which is our RM, has got 50 ohms. So this is your meter in this case, and this is your shunt. So which idea can I use to calculate the shunt resistor that is connected in parallel in this case? All right. So we can apply the concept to say the voltages in parallel are the same, but provided that we have the current of the shunt. To calculate the current across the shunt, we can use our Kirchhoff's law. The current flowing is into the junction is equal to the current flowing away from the junction, which means these two currents, if we add them, they must give us 1,5. So to find the shunt current, we can simply subtract this. All right. So this is the shunt current. All right. Let me just change this one to pen. So to find this shunt current, we can simply subtract from the total current the meter reading, which is the current across the meter of 10 milliamps. So that is going to be 1,5 minus 10 times milli means to the exponent of what? -3. So this is going to give us the current across the shunt resistor, which is going to be 1,49 amps. But the voltages, remember, in parallel, the voltages are the same. So using the idea of that the voltages are the same, we are going to have voltage from current times resistance. Remember, current times resistance gives us what? Gives us voltage. So this is the same as the voltage that we are going to have across the shunt resistor, which is from the shunt current times the shunt resistor. This gives us a voltage drop. So to calculate RSH, we can divide by the shunt current both sides by the shunt current both sides. So this gives us the resistor across the shunt. That is our shunt resistance of IM, which is the current across the meter of 10 times 10 to the power minus 3 times the resistor or the resistance, which is the internal resistance of the meter in this case, which is 50 over the shunt current, the one that we calculated at this point, this shunt current of 1,1,49 amps. So this can give us the resistance across the shunt. So making sure of our values on our calculator, this is going to give us 0.3355. So this is going to be 0.34 to 2 decimal places as per the instruction of the question paper. Remember, we are told that our answers are supposed to be to 2 decimal places. So it is going to be 0.34 ohms. All right, so that was the question on measuring instruments. All right, measuring instruments having a total of 3 marks. So you just need to know this part, or even to apply this part also that we are given. Let me check here is how it is given, so that sometimes you can manipulate the formulas that you are given in this case, or unfortunately you are not given for this one. So you're supposed to know this idea. That's why I prefer drawing this diagram so that you understand how to manipulate your formulas. But sometimes you might be given these formulas, this final formula, sometimes you are not like totally you're not given. So it means know how to formulate from the original diagram to say in parallel, the voltages are the same. So I'm using the voltage across the shunt resistor equal to voltage across the meter. The meter is the one that is your galvanometer, this one, which has got an internal resistance of 50 ohms. All right. So that was it, guys, on question number 10, which is on renewable energy and electrical reticulation. So in other papers, you are given these parts separately, renewable energy separately, electrical reticulation separately. All right. On 10.1, we are given to name 4 types of non-renewable energy sources. Non-renewable, the energy that we can't renew. What are the sources? All right. So the sources can be from sun, can be from coal, natural gas, oil, nuclear energy. So these are the ones that we have in this case. All right. I hope we saw these ones. We move on to the other part, which is 10.2. An electrical reticulation network is divided into 4 sections. Name them. Okay, what are the sections which made an electrical reticulation network in this case? All right. So we have got in this case the generation. Okay, let me show you the generation, the transmission, the distribution, and the utilization. These are the stages or the important phases that we have in the electrical reticulation network. Okay, these are the most important sections, 4 sections which are given. All right, on 10.3, we are given to choose a term from column B. So your answers are supposed to be taken from column B. This is your column B. From this column, we just write the answer from A to F, which matches to what is in column A. All right, so column A is having a certain description. Then you take your answer from column B. All right, so on column A, we are given the first part on 10.31, that is the conversion of energy from flowing water into electricity. What is it when we change water to electricity? That is hydro water to electric. Okay, so that's hydroelectric. 10.32, the carrying of electricity from transmission to consumers. That is the transfer from the transmission to consumers. What is it? What is the process? That is the distribution. All right, so this is the distribution. So this is our C. Then an electrical power line that transfers electrical energy from the distribution substation to the distribution transformers. What is the electrical power line that is referred? That is the feeder in this case, which is A. All right. On 10.34, a mechanical source of angular motion. What is the source where we have angular motion? This is a prime mover. All right, which is on B. All right, so these are the typical questions that we are given, guys, on on our final exams, this is what we expect to be asked. Typical questions of this nature, from calculations to theory. And it's best that you work with more question papers, because as we can see from our department, it's a repetition always. The question papers are being recycled now and again. So we have to work with more question papers, work with more revisions, as it is a repetition like that. It can be an advantage if you study more of your question papers, or if you revise more of the question papers that you have. But for now, that's what we had, guys, from Meson African Motives, working on electoral trade theory N2 from Meson African Motives. Till we meet again.